In this video, I am going to do an example of how to evaluate a piecewise-defined function. We've looked at piecewise-defined functions before, and this time we're going to look at it in the context of polynomials. So let me share my screen so we can take a look. The example is in Desmos. And here you can see that I have represented my piecewise-defined function by restricting the domain for three different polynomials. This is a quadratic function, so it has degree 2 and leading coefficient 1. This is a cubic function, degree 3 with coefficient of 1. And this is a linear function with degree 1 and leading coefficient -1. And I've restricted the domain because remember, with the piecewise defined function, you can't overlap the functions, otherwise it won't be a function anymore. You have to piece them together over specified intervals. These are intervals. This is the interval of all real numbers less than 0. Here we have the interval from 0, including 0, up to 2, but not including 2. And then we have the interval for all real numbers greater than or equal to 2. So when you're evaluating a piecewise defined function, you have to look and see where is the value of x that you're plugging into your function. What interval does that lie in? And then you pick the appropriate function to evaluate. So here's the graph of this piecewise defined function. So here we have the x-axis, and the interval from -infinity to 0 ends at this point on the x-axis. And so the red is the quadratic function. And then at 0 on the x-axis, it picks up 0 between 0 and 2. We have the next function, which is our cubic. And then finally, the linear function, which picks up after 2 and including 2. So here we have our functions piecewise together. Now, you might look at the resulting function and think, oh, that's also a polynomial. Actually, it's not. It turns out that in order for a function to be a polynomial, it has to be smooth. So there can't be any corners in your graph. So it has to be smoothly connected. All right, and there also cannot be any breaks in your graph. So the resulting function is not a polynomial, although it is continuous because I can draw this without lifting my pencil. So it is continuous. It's just not a polynomial. These separately are polynomials, but together you've got these corners here, and even though they're joined at the corners, because of those corners, they're not smooth. It's not smooth. All polynomials are smooth. Okay, so let's suppose we want to evaluate a function. Let's suppose we want to evaluate it at x equal -1. Then -1 is less than 0. So we are going to plug -1 here for this in this function, and -1 squared is 1, and then we subtract 1, it's 0. And you can see that if I hover over this point at -1, the output, the y value, is 0. So evaluating this piecewise defined function at -1 gives us 0. Now let's suppose we want to evaluate it at 1. Then we look here, 1 lies between 0 and 2, so we plug it into this function here. And we have 1 cubed, that's 1, minus 3x1 squared, that's -3, so that's -2, plus 3 times 1, that's going to be 5. Wait a minute, I'm sorry. 1 minus 3 is -2, plus 3 is going to be 1, and then -1 is 0. And you can see right here that we have this point 1, and we plug it in and we get 0. Moving on, if we want to evaluate, let's say, the function at 6, all right, then we're going to go 6. We're going to look at these intervals and see that 6 is greater than or equal to 2. So we're going to plug in 6 here, and it's going to be y equals -6 plus 3, so it's -3. And you can see at 6, this point, the output, let's see if I can hover over that the right the output for 6 is minus 3. Okay, so that's how we evaluate piecewise defined functions.